So continuing with circuit complexity. So just to summarize what we did last time, we went through the definition of circuits and how circuits can be used to compute functions. And now we defined a complexity class. We defined size S of n to be the family of languages computed by S of n sized circuit families. And Shannon's theorem says that all languages lie in size 2 to the n divided by n. So which is nice that we can actually capture, in this case really an optimal bound for the circuit size complexity of any function. And then we define p slash poly to be all languages computable by polynomial sized circuits. That's p slash poly. So what this means is that if L is in p slash poly, we can construct, which is, instead of saying we can construct, I should really say there exist. Because it doesn't really tell you how you can construct them. It says that they exist. And then there is the non-uniform hierarchy theorem, which basically says that just as for deterministic time and for space, we have a hierarchy theorem for size, that the languages that are computed by the size like 4 SN size circuits is a strict superset of the languages computed by size S of n circuits, and you can use Shannon's theorem to prove this. So let us now relate circuit complexity to time complexity and the classes that we know and love like P and NP. So we can ask, P is the set of languages that have efficient algorithms, and p slash poly is the set of languages that have, I'll sort of put this in quotes, I'll say efficient circuits. And so it's natural to ask, what is the relationship between P and P slash poly? And so for the first theorem of today, what we'll prove is that P is actually a strict subset of P slash poly. And the proof is basically, the Cook-Levin construction. So consider L in P and let L sub n be all the elements in L whose length is n. These are the strings in L whose length is n. So I'll sort of draw a picture. So remember the Tableau method. And so one has the Tableau here. And because L is in P, we know that there is a Turing machine M deciding L that runs in n to the k time, and k is just some constant. So we can take the Tableau being n to the k times n to the k, and usually in the Tableau what happens is we can say x is written here. So this is only of length n. That's what x is, and all of these are going to be blanks. And if we look at the Tableau, So let T of T, and I'll say the position, I'll just call it S. So what I mean is I'm looking at time step T, I'm looking at the Sth position, and T of Ts is basically the symbol, at time T, and the position S of the configuration. So we know that in any tableau, if we look at the tableau here, we know that this cell is just a function of the symbols in these three cells. And this is some fixed function that depends on the Turing machine. So T, little t, and S is just some function of capital T, T minus 1, S minus 1, capital T, T of T minus 1, S, and T of T minus 1, S plus 1. And this is the locality of the Turing machine, meaning that we just need to check, is there a head in here, and if there is a head, then what transition function to use. And this is important because M is deterministic, F is a fixed function. So this is important. In the proof of the Cook-Levin theorem, there was no explicit function because of the non-determinism in the Turing machine. So depending on the symbols there are multiple possible choices of what could go into the next cell, into capital T, Ts. But because the function is deterministic, it doesn't, we can explicitly, the Turing machine is deterministic, there exists this explicit function S. And then, so now what we can say is, using binary encodings for the symbols, F can be represented as a circuit with many outputs. And that's because you need to output the encoding of the symbol there, and that encoding may require many bits, but it's still some constant. So all of these are constants. As a circuit, what is important is of constant size. So the function that takes three symbols on the tableau, three consecutive symbols on the tableau, or contiguous singles on the tableau, and outputs the next appropriate corresponding symbol, can be represented by a function of constant size. A circuit of constant size, because this is just some explicit function. One can just write down the truth table, and that truth table will depend on the Turing machine M. All right, so is this clear? So essentially, for every cell in the tableau, we can write it as a function of, in some sense, the previous three cells, and that is represented by a circuit. We stitch together all those circuits. We simply put all the circuits together, and we will get one big circuit that computes the entire output tape, from which we can then make another circuit just to determine whether the state is accepting or not. Okay, I'll write this down, but I want to make sure that the logic is clear. So any questions about this? And I will write down too. But any questions about the basic logic? All right, let me write this down. So another way pictorially to think about this is here's the tableau. And for every cell, we're going to actually construct a little circuit, or it's actually like a collection of circuits, because each of these is going to output. It's going to take in all of these bits over here, and it's going to output some configuration. So this I'll think of as some circuit, and we simply put it all together. We have many copies of the circuit, and each of which feeds their outputs to more copies of the circuit. And the circuit is exactly the circuit that computes F. So we can put it all down.
Quick question.
Yes? Yes.
For the, we're saying that we can make a circuit using the previous three, or like the previous value and the neighboring two values.
Yes.
Next value of it.
Yes.
But what about like if the head of the Turing machine has some state associated with it as well? That's not represented in this tableau.
The head has a state, you mean, so remember that the tableau is really like writing down the entire configuration. So the way we write it down is it's not just the tape, but it's the tape with the head at a particular position. And wherever the head is, we put a symbol for the state.
I see. Okay.
Maybe I'm misunderstanding your question.
No, I think, yeah, actually that does answer it, I believe, yeah. Great.
Right, so maybe let's just recall what the tableau is. So remember that we can represent the state, the instantaneous state of the Turing machine as a bunch of tape symbols, the head, which is at a particular state. So we write down the state, and then we do, we write down the rest of the tape, and we imagine that the head is pointing to the next symbol. So the configuration essentially stores all the information about the Turing machine at that point. And the next configuration, the thing to observe is that every symbol only depends on like 3 symbols in the previous tableau, the previous configuration. And every symbol in the configuration depends on 3 symbols in the previous configuration. Does that answer your question?
Yeah, pretty much. I forgot that the tape head itself is put onto this as well.
Yes,
like
yes.
Represent it as a cell itself.
Yeah. So putting all these small O of 1 sized circuits together, we get a O of n to the 2k sized circuit, right? And it's O of n to the 2k because that's how many symbols there are in the tableau. This tableau has size n to the 2k, n to the k times n to the k, and each symbol requires a circuit of constant size, so we just stitch together all those circuits. And we have an O of n to the 2k sized circuit that computes the final configuration the input is x of length n, right? Because the input determines the first configuration. So the input is going to have basically the original, the starting state Q in the beginning, and then there are going to be these n bits that represent the input n, and then you've got a bunch of spaces or blanks to represent the rest of the tape. And so the only input is really X. Everything else is pre-configured. So you pre-configure Q, and this is the starting state of the Turing machine, and you pre-configure the spaces, and then all you need to do to get an input is X. You stick X in. There is going to be this large circuit, or I guess it's not large, but it's n to the 2k sized circuit, and the final output of the circuit is the final configuration. And of course, to determine if the Turing machine accepts, we have a circuit that determines if the final state is accepting. And this is again easy to construct because the circuit, we could just have a separate circuit for every symbol and saying, is this an accepting state? And just take the AND of all of those, or I guess the OR of all of those. Take the OR of all of those. Right? So for every symbol, we can determine, is this an accepting state? So we have a circuit that determines if the final state is accepting. And so what we have pictorially is, we have all of these circuits sort of in an array where, this is getting inputs from these, and this is getting inputs from these, so on and so forth. So we set everything up, and then finally we put it all together into one circuit that just outputs yes or no, depending on the very final configuration. And so this, and then here you have the input X. Here is Q0. And so this becomes the entire circuit. Right? So there exists a big O of n to the 2k sized circuit that accepts Ln, which are just the strings in the language of size n. And so hence P is a subset of P/poly. P, it's a subset of P/poly. Okay, any questions about this? Now, to show that P is a strict subset of P/poly, I can give you simple construction that shows that P/poly contains undecidable languages. And obviously, P does not contain any undecidable language. So a very simple language that is contained in P/poly, which is undecidable, is, I'll just call it unary halt. And so what unary halt is, it's the language 1 to the n, where n is equal to the encoding of mx, where m halts on x. So this is a unary language. So it's just saying that treat every instance of the halting problem as an integer, as a positive integer or a non-negative integer, and then consider the language where you basically encode that in unary as opposed to binary. So this is unary halt. And a simple exercise is that all unary languages, by unary I mean it basically is of the form 1 to the n for various values of n. All unary languages are in P/poly. It's quite trivial because all the circuit has to do for every n, it's kind of hard coded if it's in the language or not in the language. And so all the circuit has to do is to determine if all of the symbols are 1. right? Because remember, a circuit family is like a different circuit for every value of n. So that different circuit could simply encode, would simply be whether 1 to the n is in unary halt or not. And so P is a strict subset of P/poly.
Why aren't we able to just simulate a polynomial sized circuit with a Turing machine?
You can simulate every circuit with a Turing machine, but note that a circuit family is an infinite set of circuits. So there isn't one Turing machine that can capture all of its behavior. So recall that in a circuit family, so let me just sort of end this and I'll come back to that. So what is a circuit family? A circuit family is something of this form, where C of n is a circuit for inputs of size n. And as we discussed in the previous lecture, every language has a circuit family that computes it. Every language. But that doesn't mean that there's a Turing machine that can, decide every language, because the description of C is infinite. The description of C, or script C, is potentially infinite, while a Turing machine has a finite description. And so the description of the circuit family that computes unary halt is an infinite description. On the other hand, there cannot be any Turing machine that can sort of decide the same language. For any individual circuit, so if you fix n, you can construct a Turing machine that simulates the behavior of that circuit. But essentially, you would need infinitely many Turing machines to be able to simulate the circuit family. Does that make sense?
So for unary halts, is the idea that so you can encode an m and an x, and that results in some number n, and then there will always be some circuit in some kind of circuit family that will compute whether n is the right number or whether it has the right number of ones.
No. It's even simpler. It's even simpler. So the thing is, for every n, 1 to the n is either in unary halt or not. Right? I mean, that's just trivially. Like for every n, either it's in unary halt or it's not.
Right.
So let's say it is. So for that n, create the following circuit. It simply checks whether all the bits are 1 and then accepts.
Well, I don't understand why you even need to make unary halt. Like, why can't you just have a circuit that checks to see if n is the right number or not?
What do you mean by n is the right number?
Because aren't we essentially taking this number resulting from the encoding of m to x, and then we're basically transcribing it into unary, right?
That's what the language is, right?
But then why? Well, what is it? I mean, can't you just say the same? Is the same argument essentially applicable to just checking whether n is the right, like having a circuit that accepts only, like having a circuit in some circuit family that accepts a certain n where m halts on x, and then without transcribing it into or without worrying about it being transcribed into unary, and then having a circuit that doesn't accept other n's, right?
So no, the problem is your circuit has to deal. There has to be one circuit for all inputs of a given length.
Okay.
So if you were to not do the unary part, you could have multiple different encodings of m and x which all have the same length.
Oh, okay.
And you would need to have one circuit that sort of figured out which of those are in the halting language, which we don't know how to do.
Oh, sure.
You see, at that point, you'll bump back into undecidability.
So unary is sort of unique.
Unary is unique. Basically, it says that every single... Okay, so here's the way to think about it, right? A Turing machine has to handle inputs of all lengths. A circuit has to handle all inputs of a fixed length.
Right.
And what I'm doing here is to ensure that for every length, there's at most one string in the language.
I see.
So it simply becomes a decision of which of the ends does the circuit family need to accept. And a circuit family can accept any subset of ends because you're allowed to hard code for any specific value of n. You can construct a circuit.
I see. So if we didn't transcribe it to unary, then there could be multiple combinations of Turing machines and inputs that would result in that n. But if we do transcribe it to unary, there's only one representation for each, and then each circuit, there's only one circuit that will accept every instance of the language.
Right. So let me just clarify what you said. I mean, what happens in this case is there could be, so for every different m and x, you'll get a different n, of course.
Right.
But on the other hand, the encoding of those ends may have the same length.
Right.
In which case, there's one circuit that's going to have to deal with many of them.
Right.
The way I've done the encoding here is that for every length, there's only one instance of the halting problem that is encoded to it. For every length. Which means that the circuit that does this, it's almost trivial that there is a circuit family. So what is a circuit going to do? Circuit first checks, are all the inputs 1? If they're not, it just rejects, right? That's a simple part. So now let's just say the circuit has figured out that the thing is unary. Now it needs to decide whether to accept or reject. Now this decision to accept or reject can be different for different n. We can hard code this into the circuit family.
I see. So you need to have, it's because that there is a circuit family for each, you can choose a circuit family.
Exactly.
For each, right.
You can choose the circuit family for this language.
I see.
The description of that circuit family is infinite. Is potentially infinite. Right? If you wanted to explicitly write down what these circuits are, then that is potentially infinite because we know that the halting problem is not decidable.
Right.
Indeed, I don't even have to do this with the halting language. I can do it with any undecidable language. I can take any undecidable language, encode the undecidable language in unary, and then that language would be in p/poly because the polynomial part is simply to determine whether all the bits are 1, which can be just done in a linear sized circuit.
So essentially the reason we're saying that this is a strict subset is because the circuit family itself, there was no requirement that it is also computable.
Yes, exactly. There is no requirement in the definition of p/poly. There's nothing that says that the circuit family has to be computable.
Now, if we were to say that it was computable.
Okay, good. So this is coming to the next point. This is actually something I was going to skip over, but given your questions, I'm going to talk about that now. It's a good point, but good. So let's hold that thought.
Well, I guess at least to finish the thing I was going to say, if it's polynomial time computable as well, then they're equal.
Then they're equal, exactly. So this is what I was going to say. And I was going to give you a technical term for that. If the circuit family is itself computable in polynomial time, then P is equal to p/poly. Exactly. So, there's a minor digression that I would like to make before I go like I leave this. What I want to say is that if you look at the circuit, it's actually even better. This what I constructed here is that the circuit C constructed in the above proof. And what is that circuit? That circuit is this circuit, C. And maybe I should call it C sub n. So the circuit C sub n constructed in the above proof is actually implicitly log space computable. Right? The circuit is actually computable in log space because actually the circuit is easy to compute. The circuit over here has nothing to do with x. The circuit is just a function of the Turing machine. So we can, given x, so let me now write down what I was going to say. Given x, we can compute in log space a circuit C such that x is in P if and only if C of x is 1. This is exactly what we did. Now, what we did in the proof was simply said that instead of this, we said there exists a circuit. But we said something slightly different, but it's actually the same. We said that for all x of a given length, there exists a circuit such that, I'm sorry, x is in the language. X is in the language. So what we said is there exists a circuit. But actually, we can also, given x, we can compute in log space. We can compute a circuit such that x is in L if and only if C of x is in 1. Okay, what I'm going to now state is basically try to convert this to a language, and we actually get a very interesting definition of completeness within P. So let me consider the language circuit eval, which is all encodings of C and x such that C of x is 1. Right? This is just circuit eval is simply the language of evaluating a circuit. Clearly this is in P because you can run the circuit in polynomial time. What we just proved, or I didn't write down the proof explicitly, but basically what this idea shows is that for all L in P, L has a log space reduction to circuit eval. Therefore, circuit eval is P complete. It's like complete within P, because every other language in P can be log space reduced to this. And sort of the main punchline or the main importance of this, a corollary of this, is that L is equal to P if and only if circuit eval is in L. So what this is saying is, if you're trying to understand if all of P can be computed in log space, which we don't think is true, it suffices just to look at the circuit evaluation problem. So this is nice, right? This is exactly what NP completeness gave us, that you can now focus on one problem when you're trying to understand P versus NP. And over here, if you're trying to understand L versus P, it suffices to look at one problem, and that is the circuit eval problem. Okay? Any questions about this? All right. So actually, I'm gonna jump over what I said I would jump over, which is this issue of circuits that can be computed by a Turing machine. This issue that was raised, and I will return to this later because there is another topic that I want to finish, and if I have time at the end, I'll return to it, or I can come to it in the next lecture if you're interested. So, I mean, there wasn't much more I was going to say other than there is a notion of uniform circuits, which are those computed by a Turing machine. What I want to do is, given the discussion that we have of P versus P slash poly, we can also ask P slash poly versus NP. So one might say maybe P is not equal to NP, but NP has polynomial size circuits, meaning that for SAT, for every size, you can come up with a circuit that solves an efficient circuit. Another way to think of P slash poly is like giving a different efficient algorithm for every size n. So this is like saying P slash poly gives you, if you wanted to show that a language is in P slash poly, or if you're trying to understand what P slash poly is, there's a lot more slack than P. A polynomial time algorithm has to work for all inputs. P slash poly says you can give a different algorithm for every size n as long as the algorithm code has length polynomial in n. So this is because we just discussed you can always convert an algorithm to a circuit. So when you're saying there exists a circuit, you can also say there exists an algorithm. We can think of P slash poly as actually an algorithm where you're allowed to increase the code length. I mean, this is, I'm fudging over a few details, but I'm trying to sort of tell you why, P slash poly is more powerful. You can think of it as almost like you're allowed to give it more and more complex pieces of code for larger sizes. Whereas when you think of an algorithm, you have to give one algorithm for all sizes. So an approach, and this was considered very promising for decades, and I'll actually show you that at some point, it's how it seems like we're very close to P versus NP. An approach to P versus NP is proving, actually sometimes it helps to prove something harder. Let's try to prove that NP is not in P slash poly. So if NP is not in P slash poly, then clearly NP is not in P, because P is contained in P slash poly. And so a grand challenge is to prove what's called circuit lower bounds for NP, is to prove that there don't exist small circuits that compute SAT. And so towards this, a very important theorem of Karp-Lipton from 1980 says if NP is contained in P slash poly, then the polynomial hierarchy collapses to sigma 2. So this is really, when you first look at this, this is surprising because the conclusion has nothing to do with circuits. So what this is saying is, if you don't think that the polynomial hierarchy collapses, if you think the polynomial hierarchy does not collapse, then you conclude that NP is not in P/poly. Of course, if the polynomial hierarchy doesn't collapse, then it's obvious that P is not equal to NP. Like if P is equal to NP, the polynomial hierarchy collapses. But this is saying that even if NP is in P/poly, the polynomial hierarchy collapses. Any questions about the statement of the theorem? So we're going to do the proof after this, but any questions about the statement and what this means? So it's a good time to pause for a few minutes. We can take a break for a couple minutes, and I'll answer any questions that you have so far. So let's continue with the proof of the Karp-Lipton theorem. So, okay, let's assume that NP is a subset of P/poly. We will prove that pi2 is actually contained in sigma 2. So remember, pi2, this isn't exactly what I'm saying, but this is kind of like saying that co-NP is contained in NP. Although it's sigma 2 and pi2, which is like the next level of the hierarchy. But what we're saying is kind of like co-NP is going to be equal to NP. But it's sigma 2 is equal to pi2. Okay, so let's consider pi2 sat. Right? And so what is pi2 sat? We know that it's all encodings of phi, and I'll say x1, x2. So all formulas such that for all x1 and somewhat abusing notation, I am going to use n for the length of x1, although it doesn't really matter. I mean, it's basically some polynomial in the encoding length, and you could think of this as being some polynomial of n, so it's all the same, such that there exists an x2. We can just assume that these lengths are the same because you can make one longer than the other and it can ignore all these, it can ignore those variables. So remember, this is a formula, right? This is some Boolean formula, right? So it's pi2 sat, which is for all x1 there exists an x2 such that phi x1 x2 is true. This is pi2 sat. So, and we know that pi2 sat is pi2p complete. This was one of the fundamental statements about the polynomial hierarchy. So if we can show that pi2 sat is in sigma 2, we'll be done. So we will show that pi2 sat is contained in sigma 2. Okay, that's what we will show. So let's look at just writing down what pi2 sat is. So I'm going to sketch out the main idea of the proof, and once I write the sketch, let's discuss the sketch, and then I'll write down more formalism. So it's just saying this is all phi, encodings of all phi, such that for all x1 there exists an x2 such that phi x1 x2 is true. So let's look at this part. So in this, x1 is fixed, right, because it's quantified. x1 is quantified. So we're just saying there exists an x2 such that phi x1 x2 is true, but x1 is fixed. So this is just an instance of SAT. This is an instance of SAT. So in other words, we're saying phi is in pi 2 SAT. We're looking at some phi in pi 2 SAT. And what this means is that for all x1, we need to solve an instance of SAT. So another way to look at this is, suppose you wanted to determine if phi is in pi 2 SAT. So what you would need to do is, naively, for all x1, so for all settings of x1, you need to solve SAT. Right? And that's why we think the polynomial hierarchy is harder than NP, because in NP you just need to solve one instance of SAT, and here it's like you need to solve an exponentially many instances of SAT. This doesn't give an algorithm, but just as a thought experiment. How would we solve this instance of SAT? Well, we say, okay, we assume that NP was in P slash poly. NP is in P slash poly. So there exists some polynomial sized circuit solving SAT. So what I mean by that is, in this case, for all x1, we need to see if phi x1 x2 is in SAT. Remember, the x1 has been fixed, is quantified. Or we can say is. So let's just say that we're just saying for all x1, we need to check that the encoding of phi x1, and I'll just call it x, if this is in SAT. So this has some length p of n. And there exists some polynomial sized circuit solving SAT. So there is a circuit which I'll call C of size q of n, which is again some polynomial, solving SAT instances of length Pn. Meaning that there is some circuit. Now we don't know what it is, but we know that there exists a circuit. So what does it mean that for all x1, phi of x1 comma x is in SAT? That's just saying that for all x1, C, when given the encoding of phi x1 x, is 1. That's really what it means for phi to be in pi 2 SAT. It means that for all x1, which is the first argument, you fix the first argument, and then you feed whatever results into C, which is a circuit that solves SAT. Okay? Now C has size q of n. We don't know what the circuit is, but we can use non-determinism to actually guess the circuit. So we can say that phi is in pi 2 SAT if there exists some C whose encoding length is q of n. which is like the circuit size. That's like the encoding length. So this, we can, let me call this Q prime and call this Q. So there is some circuit whose encoding length is Q of n. So we non-deterministically actually guess what the circuit is. And then we say for all x1, 0, 1 to the n, C of the encoding of phi x1 x is 1. Like this is the approach. But this is now looking like sigma 2. Remember, in pi 2, we start with an universal quantifier and then have an existential quantifier. But here, what we have is we have an existential quantifier and then a universal quantifier. So this is sigma 2. And therefore, we conclude that the latter part shows that pi 2 sat is actually in sigma 2. And then this will complete the proof. So we use the non-determinism, the initial existential quantifier, to actually guess what the circuit is. And once you guess the circuit, then you say, okay, then for all x1, you use that circuit to determine if it's satisfiable or not. This is the idea. And we're just going to make this formal. Any questions about the idea?
Wait, I didn't understand why we had to specify why we have Q of n and then we have Q prime of n.
So, okay, so technically, when I say it's a circuit of size Q of n, that's not the size of the encoding per se, that's the size in terms of the number of gates.
Oh.
So it's up to a constant, right? So Qn is just some constant factor of Q prime n.
Oh, okay, I see. So the size of the circuit is not necessarily the exact same as the encoding of the circuit.
Is not, but it's it's up to some polynomial factors. Probably there's like an extra log n factor or something because you have to specify the adjacency list, or the adjacency matrix or adjacency list, and you have to specify like the gates and what they are. So this is some extra encoding that you have to tack on to it.
Sure.
But it's still polynomial. The point is there's a polynomial size circuit. So a sigma 2 machine in some sense can use its non-determinism. So think of this as a sigma 2 machine. And it uses its non-determinism, its initial non-determinism, to actually guess the circuit that solves SAT. It's really clever. And once you guess the circuit that solves SAT, then you use that circuit. So there's a fudge here. There's some, think about it carefully, you'll see that there's a problem, or there's some part of this that is not clear. What is it? What's the issue with the proof idea?
Are we allowed to do that non-determinism?
Sure, non-deterministically, if you look at what sigma 2 as a language is, it says that there exists such that for all and some Turing machine does something. Right? And
okay, that's fair.
Right? So there is nothing, I didn't fudge anything with sigma 2. Indeed, I want to say not if, but if and only if. Right? That's what I need to show that this is in pi 2. I need to do if and only if. So where's the catch? So one part actually is legit. The legit part is suppose phi is in pi 2 sat. Suppose phi is in pi 2 sat. Then we know that there exists this circuit and all of this works out. What if phi is not in pi 2 sat?
is it possible? Is the problem perhaps that well, if phi is not in pi2 sat, then either then it could either be the case that there exists fails, or that the for all fails. For all, it might not be the case that for all x1 there exists.
So good. Okay, so let's go back to this definition then, shall we? So we say if phi is in pi2 sat, then for all x1, phi of x1 x should be in sat. Which means that if phi is not in pi2 sat, there exists some x1 such that this is not satisfiable. Right? There has to exist some x1 so that this is not satisfiable. So there must exist an x1 so that this is not satisfiable. See, here's the problem. How do you know that the circuit actually solves sat? So it's like thinking of it, you non-deterministically guess a circuit. But you don't know if the circuit actually solves sat. So maybe it's always returning 1. What if the circuit that you guess always returns 1? Well, then this is sort of trivially true. Does that make sense? It seems that this would be true for anything because, okay, if you choose the circuit that solves sat, then it's legitimate. But suppose the existential, the non-determinism, chooses a circuit that just returns 1 all the time.
Oh, right. All we said about the circuit was that it had to have this property. Like we didn't actually say that the circuit had to, be a sat-solving circuit.
Exactly. We don't know if the sat... And how is... So this Turing machine, whatever is being done here, has to be polynomial time. So how on earth is this polynomial time machine going to actually determine that C solves sat? So think of this as like your machine M. Maybe C does not solve sat. Think of the non-determinism as an interaction with someone. The non-determinism is like a certificate, right? So there is a certificate, it's providing you the circuit. But the the polynomial time machine has no way of verifying the certificate, where the certificate now is actually the circuit that solves sat. Right? M needs to verify that C is a sat solver. Or actually, I should say a sat decider. I kind of gave away the next step. So in some sense, this doesn't work, because just because there's a circuit that solves sat doesn't really help. But now let's go one step further. Suppose the circuit doesn't just return yes or no. The circuit actually returns a satisfying assignment. So suppose the circuit returns a satisfying assignment, then this would work, because M would get the satisfying assignment and check if the satisfying assignment is actually satisfying this instance. Remember, because sat is an NP, in some sense, instead of asking the circuit to decide sat, we could ask for the circuit to return the certificate. So towards that, I'm just going to prove a claim. Suppose C is a circuit of size S that decides sat with at most n variables. Then there exists a circuit C prime of size O of S plus n square that outputs a satisfying assignment if one exists. Okay, so we're going to need this claim. So we're saying, suppose there exists a polynomial sized circuit that decides SAT. We can use that to construct a polynomial sized circuit that actually outputs a satisfying assignment. And once you see the idea, it's not that complicated. It's called the self-reducibility of SAT. So the proof is, I'm going to actually give you an algorithm. And remember, using the P and P/poly construction, we can convert an algorithm into a circuit. So consider the following algorithm. Actually, it's S times n. But it doesn't matter, right? So it's O of S square n square. It's all polynomial. So consider the following algorithm to find a satisfying assignment. So, assume that C of phi is equal to 1. So let's assume that actually the formula is satisfiable. So what we'll do is we'll say so we have a circuit that decides SAT. We can simply say if the circuit phi, where we set the first variable to 0 and keep all the other variables. So we can apply the circuit on the formula where we set the first variable to 0. So if this is 1, we can set x1 to 0 because we know that when you set the first variable to 0, there exists a satisfying assignment. Else, set x1 to 1 and repeat for all variables. Like you do the setting and then you repeat. So as you keep doing this, we will eventually set all the variables. Does this make sense? So if you gave me a circuit that decides satisfiability, I can actually find a satisfying assignment. Because what I would do is I would set a variable to 0 and I get a SAT instance. Right? I basically set the variable to 0, I get a formula. Is this satisfiable? If it is, then I can just set the first variable to 0. If it isn't, and there actually exists a satisfying assignment, then the first variable must have been set to 1 in any satisfying assignment. And doing this, I can repeat for all variables, and I end up with an assignment. And indeed, like this is what happens in a lot of SAT solvers, right? If you can decide, then you can kind of use this to construct an assignment. Any questions? Is this clear?
This is assuming that we already know that a formula is satisfiable.
You're right. So if the formula, so think of what the circuit C prime does, is it's going to output two things. It's going to say either it's satisfiable and give you a satisfying assignment, or it says it's not satisfiable. Right. So obviously, yeah, if there's no satisfying assignment, but then you already have a circuit that determines if there is a satisfying assignment or not.
And we know that C is, it does decide SAT. Like, it's not just a case where, we don't know whether C is just outputting 1 all the time.
Right. No, this is saying, suppose C is a circuit, then there exists a circuit C prime.
Okay.
But the nice thing about C prime is if we played this game with C prime, then M can actually check if C prime is bogus or not. Because C prime is going to give a satisfying assignment, so M can just go and check, is it actually a satisfying assignment?
That makes sense.
So you see, this is pretty clever, right? Basically what it says is you guess the circuit, but you also ask the circuit to give a certificate. Okay, so this, I just described an algorithm. The running time is O of S times N. It's O of S times N because you have to run the circuit. So imagine that there's an algorithm that actually ran the circuit. So the running time of that would be S. And N is because there are N repetitions for all the variables. By the P is a subset of P slash poly construction. There is a circuit of size O of S square N square that outputs a satisfying assignment. Okay. So like pictorially, okay, so now let's go back. So I'm going to write something down. I'll write down a claim here, and once we prove the claim, the theorem will follow. I'll say the original phi, and remember this phi had x1, x2. This is in pi 2 sat. If and only if the following holds, if and only if there exists some encoding of a circuit C prime whose size is 0, 1 to the S square N square, right? I'm sorry, not S square, where S I'll say is Q of N square N square, where Q of N was the encoding of a circuit that solves SAT. Q of N is the encoding of a circuit, that solves SAT. And so we know that there is a larger circuit, which is quadratic, that actually outputs a satisfying assignment. If there exists a C prime such that for all x1, so this is the existential, this is the for all, so that for all x1, phi evaluated on x1 for the first argument, that's what we had initially, on C prime, okay, so hold this, phi x1 x. So the second, remember that we're looking at instances where, because we're doing pi 2 sat, there are two parts to the input. There's the for all part and there exists part. So the for all part, of course, is whatever we had before. The there exists part, this is the satisfying assignment for this SAT instance. So we're going to use the circuit C prime to compute that satisfying input. And we're just going to plug that satisfying input into x2. So the second argument is whatever C prime outputs on the encoding of phi itself. Phi with x1 fixed. And so we have this is true. Does the statement make sense? Statement makes sense. And so now let's give the proof. So the forward direction, and this is going to be the easy part. So phi x1, x2 is in pi 2 sat. Let C prime be the circuit that outputs a satisfying assignment. So we know that the circuit exists of size, q of n square. So there's some circuit. Now, because phi of x1, x2 is in phi is in pi 2 sat, we know that for all x1, phi of x1, fixing x1 and leaving the second one open, this is satisfiable. Hence, C prime on phi x1 comma x returns a satisfying assignment, because this is satisfiable and C prime is that circuit. Hence, C prime returns a satisfying assignment. And thus, phi of x1 and the output of C is true. So for all x1, this is going to work. And this was in some sense the easy part, because we know that this is true. Now we'll actually see the other part also becomes fairly easy. So let's do the opposite direction. Suppose there exists a C prime such that for all x1, phi of x1 C prime phi of x1 x is true. Now, interestingly, it doesn't even matter what C prime is. Maybe it's a circuit that solves SAT, maybe it's a circuit that doesn't solve SAT. What's important is that this means, therefore, for all x1, phi of x1 x, where this is your x, is satisfiable. Because there is a circuit that provides some input that makes it true, so therefore phi of x1 x is satisfiable just by definition. Thus, phi is in pi 2 sat. So phi is in pi 2 sat if and only if there exists C prime such that for all x1 there's some polynomial time computation which accepts. And thus pi 2 sat is actually contained in sigma 2p, and that completes the proof. That was the end of that proof. So you'll have to go back and kind of really understand lots of the details, but the basic idea is encapsulated in the original idea that I said, that the existential is going to guess the circuit that solves SAT. And as long as we make it output a satisfying assignment, then it's easy for M to verify that that circuit is actually doing what it needs to do. So it doesn't even need to go and explicitly verify it. All it has to do is just plug in whatever that satisfying assignment is in the position of X. Right? If it gets a satisfying assignment, just plugs that in. And this is all that is required. So, popping back all the way up, the Karp-Lipton theorem says if NP is in P/poly, then pH collapses to sigma 2. It's a big open problem to actually get any kind of circuit lower bound for NP. Forget proving that it's not P/poly. Can you prove that there aren't quadratic size circuits, just n square size circuits that solve SAT? And even that's open. So what's interesting is, and this is your homework problem, and your homework problem essentially, if you solve that homework problem, I think you will understand this proof really well. It's based on similar ideas. And this is a much stronger unconditional lower bound. And it says that for all k in n, there exists a language in the polynomial hierarchy. Indeed, it's even sigma 2 is enough, that cannot be computed by an n to the k size circuit family. So remember, in the previous proof we said if NP is in P/poly, then something holds. But this is a much stronger statement. This is unconditional. It says that there is a language in the polynomial hierarchy that cannot be computed by an n to the k size circuit family for all k. This is one of the homework problems. It's challenging. I've broken it down into a few steps and I've given you hints on how to do it. The ideas are using the ideas in Karp-Lipton, where again this issue of trying to guess a circuit is crucial. So you essentially have to non-deterministically guess a circuit, make sure it has the right properties that you need, and then you can use some alternation of quantifiers to get things to work. So I want to show you how this seems like we're so close to proving P versus NP. And yet we know that we're really far. So what this is saying is that for all k, all natural numbers, the polynomial hierarchy is not contained in circuits of size n to the k. Now what is P/poly? That is just the union over all k. So we know that the polynomial hierarchy is not contained in any of these sets. If we can prove that the polynomial hierarchy is not contained in the union, so we can prove that it's not contained in any of these sets. And if we can prove that it's not contained in the union, then actually P is not equal to NP. That would give a proof that P is not equal to NP. Why? Let's take the contrapositive. If P is equal to NP, then the polynomial hierarchy is actually equal to P. Remember, the polynomial hierarchy is built through the oracle model, and if all the oracles are in P, then everything is in P. And P is definitely contained in P/poly, as we proved earlier. So we can prove this. We already know how to prove this. And the million-dollar question is whether we can prove this. Because if we prove this fact here, that pH is not in P/poly, then we prove that P is not equal to NP. And so it seems that many of these kinds of results, this statement that we can prove, this theorem, that is one of the homework problems, suggested to researchers that we are getting fairly close to proving that P is not equal to NP, because we're able to prove that the polynomial hierarchy cannot be computed by an n to the k size circuit family. And yet, that's still, as is transpired, very far off from proving that pH is not in P/poly. Because if the polynomial hierarchy is not in P/poly, then P is not equal to NP. So on that note, I'll end, and I'll take any questions that you have.